Welcome to Study Loop.
Hi, so we're trying to solve the exercise 1 of section 10.1, and the exercise is to find the torque applied onto the rod. So let's first draw out the 6 cases that we need to find. So for each case, we have a rod of 4 meters and a force of 10 Newton. And in every case, we have this fixed point pivot, this pivot O. And it's quite important is that we know every time we need to find a torque, it's always with respect to a certain point. You cannot do it without knowing which point it is. So here are the 6 different cases we need to do. And in each of these, we have F equals 10 Newton. And the rod is 4 meter. So let's first do a little bit review of how to find a torque. We know that from section 1, the formula we were given is that torque equals F times L. And this tau, the Greek letter tau, means torque. F, this F is not all that. This is the force that is perpendicular to the rod we're looking for. So in some of these cases, you can see that the force is not completely perpendicular. In that case, we have to find the component that will contribute to the torque. And L is the distance from the point to the pivot. So let's first look at case A. This is a relatively easy one because we have 90 degrees over here. That means this F is already perpendicular to the rod, so we do not need to decompose it and find the component. We can just plug into this equation and we got torque equals force is 10 Newton and L is the length of this whole rod, which is 4 meter. And that gives us 40 Newton meter. That's the unit. And let's move on to number B. In B, we have 120 degree. So in this case, we do need to decompose this force a little bit. So we can put this into a component that is tangential to the rod. So that is this part. And a component that is perpendicular to the rod. And so the component that's tangential to the rod, it does not contribute to the rotation of the rod. What it does is it only compresses the rod. But for the torque is used to describe the rotation of the rod, so only this component will contribute. And this component, we can find it by using a little bit of geometry. This is 120 degrees, that means this is 60 degrees. So this equals F times sine 60 degree. So sine 60 degree, it is, if you have a calculator, it's square root 3 over 2, or around 0.86. So F is 10 Newton, this gives us 8.6 Newton. And from that, plug into this equation again. This is the equation we'll be using over and over. We have 8.10 Newton times, again, 4 meter, because the point of contact here is 4 meters from the pivot. And that gives us an answer of 34.6 Newton per meter. So we can see this answer is smaller than 40 because we are not using this force in a most efficient way. It has an angle, and not all of the force is used to rotate this rod, and that's why this torque is smaller. Number C. This is a similar case. B and C, they're really roughly the same, except that now we have a different direction and we have a different angle. But you can see this time we are kind of pushing outward. So in this case, we still have a perpendicular component that contributes to the rotation of the rod, but the tangential component in this case is used to stretch the rod instead of compress the rod. But since we are only here to find the torque, it doesn't really matter. We still find the perpendicular component is this times F times sine 30, which gives us 5 Newton, because sine 30 is 0.5. And that gives us 5 Newton times 4 meter equals 20 Newton per meter. So that is 3. Part D. For D, now it's interesting that the point of contact is not at the end of the rod anymore. It's at the middle of it. We have 2 meters here. Since the whole rod is 4 meters, now we have 2 meters here. So this L, in this case, it really isn't 4 meters anymore. The only difference is that L is now 2 meters. But otherwise, we do the same job. This is still F times sine 60. Sine 60, as you can see. So it is, we've already calculated this, it's 8.6 Newton, but now we have 8.6 Newton times 2 meter. And that will give us 17.2 Newton per meter. So that's what we have for A, B, C, and D. Okay, now the tricky part. What happens for E and F? It might be easier to think of F. If you have this rod and you're just like pressing it at the end, it doesn't really rotate because you're just pressing it. And also just by the symmetry, if you're pressing it horizontally, it has equal chance of going up and going down because everything's symmetric. So you can't really tell. So like the most natural answer is it just doesn't move. It stays there. And indeed, and because this force really just has no component that's perpendicular to the rod, the entire force is parallel to the rod. In that case, the F we have will be 0, so the torque is 0. But what about E? Let's come back to E. In E, the force does have a vertical component. It does have a perpendicular component to the rod. But if you think about it, you're not pressing onto the rod at all. You're like pressing onto the pivot. And no matter how hard or which direction you're pressing on the pivot, the rod itself will not move. Because in this case, you have L equals 0. The point of contact exactly coincides with the pivot. There is no distance between it. You have L equals 0, and that also gives you tau equals 0. So that is the answer to this problem. From A to D, you have a torque. From E and F, you do not have a torque. You have a torque equals 0.